All right, so you will be asked some questions that just ask you to say whether something is continuous and maybe which step of the definition it fails on, but a lot of what you're going to do is actually work on making functions continuous. These will not only emphasize the continuity piece, but also just remind you about making limits exist and removable discontinuities and graphing functions. So there's lots of good stuff in here, just good mental exercise basically. So there'll be all variations on this, but what we want to do is find the value of the constant, in this case k, that will make this function continuous. So I'd say it would be good to pause and think about why it might not be continuous. One reason is because it's piecewise, so definitely at x equals 2, I'm a little concerned. The other is that one of the pieces might not be continuous, and that's definitely a possibility for a rational function. Luckily for us, x equals 2 is once again the potential problem, so we really only have to investigate what's going on at 2, and we should be in good shape. There's nowhere else that rational would have problems. Okay, so we need to take the limit as x approaches 2. The second piece of this function is really just a single point. It's saying when x is exactly equal to 2, y is exactly equal to k. So for the limit, that piece actually doesn't matter at all. It's all about the rational function. The rational function takes over anywhere but 2. So we want to take the limit as x approaches 2 of x squared minus 4 over x minus 2. And I do get a 0 when I plug 2 in, but I get a 0 on top as well. I think maybe this was in our examples list already. We can simplify this one with factoring. That's a difference of squares, so x plus 2, x minus 2. And I can cancel the x minus 2 out, which is wonderful because that's what was giving me a problem. So it looks like aside from what is in fact a removable discontinuity, a hole in the graph, the y values should be stuck right on the line y equals x plus 2. So they should be getting really close to 4 as x gets really close to 2. So the limit equals 4. So the limit exists. Step 1, check. The value of the function, n of 2, is k. So that's what we actually get to decide. This is saying, can you decide what you want the y value of that one point to be to try to make this continuous? And sometimes you might not be able to make it continuous, but this one we absolutely can. The limit exists. There's one little hole in the graph. So this is y equals x plus 2, yep, x plus 2. So the graph looks just like this, but at 2, 4, there's an open circle. So we are successful on the limit existing, successful on the function value existing. What we need is for them to be equal. So we need k to equal 4, which would mean that the second piece of our piecewise function is the 1.24 that fills in our problem. That was fairly speedy, so I think I'm going to look at the next one as well. Same directions, different function. So we want to find the value of, this time, v, that will make my function continuous. And once again, it is just a single point. I'm being given the point v2 to try and patch up this rational function, y equals x minus 4 over x minus 2. So I need to be concerned about continuity at 2 since that's where the pieces connect, and I also need to be worried again at x equals 2 because the denominator is 0 there. So let's check out the limit as x approaches 2. And notice this function is very slightly different from the last one. It's not a lot different. If we let x approach 2, I'm getting, here, let's see, x minus 4 over x minus 2. I'm getting a negative 2 over 0. That is not a removable discontinuity. So you can check out a graph on this thing. Let's see, I can probably rough sketch it for you here. It's got a vertical asymptote at 2. And it's got a horizontal asymptote at y equals 1, and it crosses at 4, 0. So it's going to look roughly like this. This is what we've got. And there is no way that I'm going to place a point. It doesn't matter if I put it here or here or here. Anywhere I put that point is not going to make this function continuous. So the answer here is that it's not possible. So it's only possible to make a function continuous if you have a removable discontinuity. All right, we'll break there for this one.